Okay, welcome everyone to this continuation of Lie theory. So today I would like to talk about Lie algebras. And next time also we'll talk about Lie algebras. Sounds a bit weird, but Lie algebras are like this linear shadow. And today I will kind of sell it to you the way I've sold it, hoping to tell you that it's like linear algebra. So the Lie algebra, like the linear approximation of the Lie group. We'll have some nice pictures as we go. But that's actually a lie. It's not really a linear approximation, but I will tell you next time why this is a lie. Today we'll just do the linear part. So it's almost the linear part if you want. But essentially the whole idea, this is not working, let me do it this way, is so why Lie algebras show up. So why in our little matrix, why do we have Lie algebras? And just a reminder here, we are most of the time essentially only thinking about Lie groups and matrix groups. We'll see several examples later. But as I said, there's a more general picture. But let's just say matrix groups. And the big picture is always that G is not linear. So the matrix group is usually not linear. I think of a torus or a sphere or something like that. A nonlinear space. And you usually take tangent space. I have a picture here, something like that, right? A nonlinear space, and you take the tangent space at a point, and somehow there's enough structure on your space that you can move the tangent space kind of around in a certain way. We don't do that today, but essentially you can do that, move it around. So the tangent space in the end tells you actually a lot about the group itself. Not just locally at the point, that's kind of by construction, because the tangent space tells you something locally around the point. But because you can move it around using the group law, essentially it tells you everything you ever want to know about the Lie group. That's a bit of a lie, but it's close to be true. And then the whole point is, so the Lie algebra is this tangent space, the best approximation to your group that you can do at any point, so why not near the identity? And then you can ask all the questions you want that are important about the Lie group. The Lie group is this group of continuous symmetries of some differential equation type space. And then you can just push that into a linear algebra problem. So you essentially take your question, maybe it's an equation or something, you take the derivative of that equation, we do that today, and you get some linear algebra problem. And it is almost true. We'll see next time it's almost true. So this for today, just think of it as a linear algebra problem. And the way this works in practice, so really the point, the best linear approximation, the tangent space, and the group questions become now linear algebra questions. And that's, who doesn't like linear algebra? Again, if you don't like linear algebra, this is probably not the video for you. That's totally fine. You can have your own preferences if you don't like linear algebra. But linear algebra is undoubtedly very powerful. Like, oh my goodness, linear algebra is so good. So if you can reformulate a nonlinear question into a linear question, I mean, that's amazing. That's what people really like to do. And how to do this in practice is really looking at our little Lie group here. In this case, in this stolen picture, the Lie group is M, just general manifold, I guess, and the tangent space is literally what you think it is. In this case, a tangent plane, because my manifold is two-dimensional. Then I get a tangent plane. And how can you describe this tangent plane? You can describe it as the velocity vectors, essentially, at the point. So you just take G, and usually kind of fun thing. Oh, I will try that. So usually people write the group like G. Okay. And the Lie algebra like this funny mass frac German G, which I probably can't. So that looks really bad. Like that, maybe? Anyway, let's not try. So this G here is usually the Lie algebra, and I'm not quite sure where the notation comes from in the sense of why did you choose that? Maybe it was just a random choice. I don't know. If you know, let me know. But anyway, usually the linear shadow is this funny G, and the group itself is a capital G. So and you will people then just use this font idea, for example, then the Lie algebra for GLN will be written, let me do that, GLN, something like that. And this was supposed to be a funny G as well. So GLN, the capital G, becomes the small one. Okay, So that's how usually how the notation works. Anyway, you can then define it as a tangent space at the identity of capital G, and it literally just the velocity vectors taken together, right? So you can do this here. I think in the previous video I did it from R, but of course I can also just do it from array or a cutoff array instead, and then just the at 0 you're at I, right? So that's all the whole point. So essentially, right, as I said, it's like the directions you can move inside G, yeah? Kind of locally around that point. So that's the Lie algebra, and let's say that's a definition of the Lie algebra. And then we have this exponential map going from the group, from the Lie algebra to the group, and there is also the logarithm, which I haven't told you about, because logarithms are a little bit fishy. So let's ignore logarithms. But this is literally just a picture. Right? So it's literally the definition, as I say here, of the Lie algebra. Right? Lie algebra, tangent at identity. Why would you do that? And I show you how to do it in practice on the next slide. Literally, it's that picture, right? It's always that picture. Here is my Lie group, if you want. And I take this approximation here, and then things about this curve here become linear equations that you can answer locally on the blue one. In general, the strategy has no chance to work. As you can see, the blue one is not a really good approximation on the black one, just locally around the point. But because you have this group structure, you can actually somehow move the questions around, and having the linear approximation is actually really, really good, right? And the rule here that you usually use is you write the defining equations for G, or whatever you want in G. Right now, I'm just literally just talking about how to compute the little Lie algebra, small g. But in general, if you have a problem in G, let's say you write the defining equation for that problem, and then you differentiate that. And that's literally what you do. And so those non-linear constraints, it's an absolutely fantastic idea. And it's kind of a miracle that it works. These non-linear constraints then become linear constraints on the tangent vector space. So you usually get a very concrete space that is like cut out by equations. And that you can study. You get to study whatever Lie subalgebras. They correspond to subsymmetries, something like that. It's a really fantastic problem. Really fantastic idea. Again, I said again, it's a miracle that it works. One of the few miracles in life. There are not many miracles in life. Life is mostly pretty bad. But literally, this is what you do. So here's how it goes. It's actually pretty easy, and I will draw a picture in a second. So let's do GLN, and you get, as I said, this is a much better font. Let's compare. I really can't draw that font. That's just what it is. Anyway, GLN, the small GLN, it's associated Lie algebra. Its tangent space is just all matrices. And how can you see that? Well, the only condition that you have is determinant not equal 0, but that's like an open condition. So let me draw a picture for you. Let me just get rid. Let me just scroll down. So here is my, I usually like to draw something like that. My little blob here, that's GLN, right? GLN. Here is identity, right? I or E, whatever. The identity matrix in this case. Yeah? Identity matrix has determinant 1. And maybe here is the set of determinant 0 things, right? Determinant equals 0. And you're away from that, and there's some little distance between them, and determinants vary continuously. So if you just look at a little whatever neighborhood of the identity, the determinant 0 condition doesn't show up at all. Yeah? You're far away from that. Determinant of the identity matrix is 1. To go to determinant 0, you have to travel some distance in that space. So that doesn't play any role. There is no real equation around the identity. So your general linear group, the general linear Lie algebra is just all matrices. Okay. Let's try another one to see how this goes. Let's try the special linear one. Special linear is determinant is 1. Okay. Special linear is determinant is 1. So the determinant is 1 is a little bit more of a tricky condition, because of course the determinant of the identity is 1. So it's really more like this same picture. Now here determinant is 0 is a bit far away, but maybe determinant is 1 is like goes like through here, right? So this is determinant equals 1. So you need to work a little bit, because now there is some condition that you have around the identity. Determinant 0 doesn't play a role, doesn't make anything, but determinant 1 does. And the way you can see that, it's actually a fun calculation. So if you take the determinant, t is now my prime time parameter, so as I move away from the identity, determinant from identity plus tx is this funny thing. So it's 1 plus t, the trace of x, and then lower order terms, or, well, lower order terms, yeah? So higher in t, so they vanish faster as t goes to 0. Yeah, so this is kind of the important part of this equation. And then, okay, you differentiate, so you want this equation, because that's the SL2 equation. Well, the only way to get that equation is that if trace is 0 in this condition, right? So hence, SLN is the space of traceless matrices. It's kind of interesting. So determinant 1 turns into trace 0. Okay? And let's have a look at some of the others. Well, so usually what this, if you think about this as being kind of the exponential map between them, usually what happens is it turns a multiplication. So here the special orthogonal group, all matrices with A times A transpose equals identity, well, it will turn, right? You have an exponential from here. You go from here to here to the exponential, so it will turn an addition into multiplication, and it will turn 0 into 1, and that's exactly what happens. And then you have some of the others, right? Like here, that condition here goes from here to here with an exponential, and you could go from here to here with a logarithm, right? A logarithm of a product would be the sum of the logarithms, and that's exactly how you go between those things. And it's kind of very interesting because this differentiation of a matrix thing, so here the standard matrix things are the first 1, 2, 3, 4, 5, is a matrix thing. Just the condition changes a little bit. It's kind of fun. So the linear approximation of something non-linear matrix is a linear matrix. It's kind of a very interesting kind of miracle that happens here, right? So there's, a priori, if you think about this problem, there's not really any reason why the tangent space of a matrix thing should be a matrix thing. Well, but it is, which makes the whole theory so nicely self-contained, right? You can just go through it just thinking about matrices, and they're the most important for applications anyway. There are some Lie algebras and some Lie groups that are not matrix groups that are important, but if you just want to think about matrix groups for now, that's totally fine. Okay, let me repeat. You essentially only need to look at conditions that matter around the identity, because we kind of locally look at the identity. Maybe this picture is a little bit better. Determinant 0 doesn't play any role. Determinant 1 does play a role. And literally you just take the derivative and you will see here, okay, we need trace to vanish. So a determinant 1 turns into trace 0, which is again this idea of turning a multiplication into an addition, or the other way around, depending on which direction you go. So there's some exponential and some logarithm going on between them. And yeah, that's literally what it is, right? So if you have an x, my little picture here that I still stole, and I forgot to add the link, so it was in the previous video. I apologize that I forgot to add it here. But anyway, this beautiful picture of, well, the exponential goes down, literally like in this way, and the logarithm, which I haven't explained, goes up. Essentially, you take your x in your, it's now a matrix, in your direction is going to motion, if you want, in your Lie algebra. You take the exponential and you get like that thing, right? You have here and you get that thing. Beautiful. So you stay inside of G, right? And that's literally where the exponential comes from. The exponential turns the allowed infinitesimal move into a general direction in your group. So the only thing that is actually missing, and I was lying about it for a long, long time, is there's some extra structure on G and that we need to keep track of. It's not just the tangent space. It's a little bit more, and I'm trying to answer that in the next video. And last time I learned, so I made last time this mistake to actually keep the sentence what is up next, which I usually don't do. But then I thought, oh, so stupid, it's a mistake, so stupid. But then I decided it's actually a good idea to have on the last slide what is up next. It's actually a good idea. So up next, where the Lie bracket comes from, which is like this extra information that we need, the lie that I told you, that actually Lie groups are not linear objects. Not quite, at least. Anyway, I hope you enjoyed this video, and I also hope to see you next time.